Good afternoon, everybody, and welcome to the final session of the day in this room. We have heat recovery, ventilator, and design. Our presenter is Steve Jollimore. Steve is a Red Seal journeyman plumber and Class B gas fitter. He has been in the HVAC trade for over 30 years, primarily as a contractor, and has been teaching since 2001. Steve is a Quality First PECHA instructor. So without further ado, I'm going to turn the microphone over to Steve. Thank you.
All right, big crowd here today.
You go to the last session. So.
Yeah. You already have my introduction, Steve Jollimore. I've been teaching for almost 20 years. I've been in the trade for pretty much 35 years. I've done estimating, service, installation, and I've been working with PECHA teaching the Forced Air Guidelines course, ventilation guidelines, HRV course, heat loss, heat gain. And I'm also the volunteer chair of the HRV committee and a co-chair of the Forced Air Committee. PECHA is the Environmental Comfort Association. We're a BC registered nonprofit, started in 2006, and we're the successor to HVCI and the Residential Hot Water Heating Association. It was established as an association for residential heating, cooling, and ventilation contractors. Many of our technical committee have over 20 years experience. I'm just going to turn my ringer off. Our officers on the board, David Hill is the president. He was showing the principles of moving air. Andrew Dick, 30 years experience. Gary Milligan, he's the other chair of the Forced Air Committee. Scott Miller used to be the president. He's with the Hydronic Committee now, and then our directors, so lots of experience. PECHA is here for the heating, cooling, and ventilation industry contractors to be a collective voice in local and provincial issues with municipal, provincial, and utility partners. Currently, the installation of HVAC systems is unregulated. Without the regulations, contractors with no skills or training are able to install systems. It's, to say, the Wild West. There's a lot of systems out there that are not working. Poorly installed HVAC systems are an industry problem. With the advancement of modern technology, the importance of choosing qualified and accredited installers becomes more important than ever. PECHA acts as an industry voice for hydronic forced air contractors, wholesale suppliers, manufacturers, and agencies, as well as engineers, utilities. PECHA's programs are developed by the industry for the industry to set a minimum standard for residential and light commercial heating and ventilation trades in BC. We offer hydronic design courses, ventilation guidelines. Our guidelines are currently the adopted standards of ventilation in BC. Forced air guidelines, which is a duct sizing, equipment selection, duct sizing, layout course. So you take the heat loss, heat gain, and it's how we design the duct systems. There's also the heat loss, heat gain course, and the heat recovery, energy recovery ventilator course, and principles of moving air, which involves this stuff here, and that's how they show how air actually travels through the duct. Our HRV, ERV certification course covers design, installation, and commissioning, and has checklists for each one. Try to keep people accountable for what they do. The main difference between an ERV and an HRV would be the core, made out of a different media. The ERV attempts to maintain the humidity in the home. So if somebody's concerned about drying out homes because of hardwood floors, expensive furniture, antiques, things like that, an ERV may be the better choice, although overventilating is usually the major cause of overdrying houses. So the HRV exhausts the moisture as well, so HRVs are a little bit better at reducing the moisture in the home as well. The equipment sizing and duct installation are the same. For the rest of this presentation, I'll just refer to HRV instead of having to say HRV, ERV. Everything else is the same except One requires a drain, one doesn't. One lowers the humidity, the other attempts to maintain it. HRVs and ERVs provide a method of balanced ventilation with the ability to recover heat from the air being exhausted. This recovered heat tempers the incoming air for occupant comfort and avoids the need for expensive electric duct heaters to temper the air as it's coming in. Nobody wants their air cold blowing on them. HRVs provide fresh air to occupants, control moisture, remove pollutants. Balanced ventilation minimizes airflow through the envelope, and they provide energy savings, minimal energy savings. The size is the same as all other ventilation systems, using table 93235 over the BC Building Code. And what we see here is it has the floor area, so that will be occupied space. So part of the way that they figure it is the floor area, and then by bedrooms as well. So if it's a 4-bedroom, 3,500 square foot house, it would need 89 CFM. It's a pretty straightforward table. The other code table that's involved in it is the one that lets us know that a kitchen needs 100 CFM intermittent. There's no continuous ratings for that. And bathrooms either have to be 49 intermittent or 20 continuous. So an HRV can provide some of the required ventilation. It can do all of it, or it doesn't even have to be in the bathroom. There's nothing that says that the HRV exhaust has to be in the bathroom. It's a pretty common place to put it because we have to put an exhaust in a bathroom anyway. But this is the basic requirements. So by code, you have to have one exhaust outlet at least 2 meters above the uppermost floor. Each bedroom has to have air ducted directly to it, either through dedicated ducting by the HRV, or we can tie it in what we call a combined system, where it's tied into the cold air return and distributes it through the furnace duct systems. When that's done, you have to leave the fan running continuously. This is a dedicated HRV system, so you notice that all of the exhausts are piped back. It goes outside. You're bringing in fresh air. It passes through a heat exchanger, one of those slides I showed earlier, the core. Passes through that where it recovers the heat that's being exhausted out. They're usually about 65 to 70% efficient. There's some European models that are even higher. And then it goes back in and distributes the fresh air to the occupants and preheats it a little bit. So that's a dedicated system. Suppliers deliver. And then partially dedicated HRV installation would be when you have a duct system. For example, a forced air furnace, heating or cooling, as long as there's ductwork that's ducted to the bedrooms and every level without a bedroom, it'd be acceptable to tie in. So with this, you have to have the fan running constantly, so the supplier delivered by the furnace ducts. You notice that it's fresh air is just tied into the return air and then goes through the system. Furnace fan must be running continuously to do this, otherwise it's not distributing the air. We'll talk about that a bit more when we talk about the energy model. There's another way called a simple installation that you'll find in most installation manuals. It's very simple. What they're doing, this is your return air going in, and what they're doing is they're taking a small amount of it, it goes through, exhausts it out, and as it's coming in, it puts the same amount of fresh air back into the system. There you go. You're not allowed to do that. That is not an acceptable method of... That's weird. Yeah, I wonder what's happening. Somebody's trying to rush us out. That's what the restaurants do when they want you to leave, right?
Yeah.
They start turning off the lights. So this is not an acceptable method. You will see it in the install instructions, but you're not allowed to do it in British Columbia. It's not an acceptable method of ventilation. What we really want to do is, at the bare minimum, exhaust the air from a different part of the house. So this wasn't very effective, so it's not really a legal install. This is our system design checklist. I'm going to go through it piece by piece. You'll notice that there's three different sections. There's the design, the installation, and then the commissioning and balancing. That way you don't get one person who knows what they're doing or a company who knows what they're doing, somebody else tries to do it, they really don't know what they're doing, and the systems don't work. So we start off with your HRV type. Just circle the one that you want, and whether it's like in the pictures before, whether it's a dedicated system or a partially dedicated system. Next box would be your required personal system ventilation. So it tells you right on the sheet. That would be table 93235. And there's a spot for additional ventilation requirements. Let's say like we were doing the bedroom count for the people. So we were doing 2 people for the master, 1 for every other bedroom. Let's say you know that there's adults living in the house and there's a couple of master bedrooms, and you know there's going to be more people than that. You could always add a little bit of extra ventilation for the people. Again, it's size through 93235, so depending on the square footage of the house and the number of bedrooms, will tell you what your minimum exhaust rate is. Here you just write down whether it's an ERV or HRV, make, model. SRE is your sensible heat recovery efficiency. We'll talk about that in a second. And then there's just a double check on the other ones. Sensible recovery efficiency is the performance quality required by the BC Building Code. We're not able to calculate that. The manufacturer calculates that and tells us what it is. Different municipalities will have different required efficiencies. The SRE must be at least 60% at an outside air temperature of 0 for locations with a 2.5% January design temperature greater than or equal to -10. That would be the lower mainland. It also, if it's colder than that, it has to have the same 60% at 0 and at least 55% at an outdoor temperature of -25 for locations with a 2.5 January temperature of less than -10. Anybody know what I'm talking about when I say the 2.5% temperature? We have to check with our municipality as well to make sure. Most of BC is 60% requirement, and Vancouver is 65%. They want a little higher efficiency, and that would be to the 0 degree because we're in a range where it's not -10, so it's not that cold temperature. What is a 2.5% January design temperature? Number of days that fall below this rate is less than 2.5%, which would be less than 1 day a month in that value. So it's not the coldest temperature, because if we designed for the coldest temperature, I remember seeing -15 in Langley. I think probably in the 20 years that I've lived here, I've probably seen almost 2 weeks of that. So would we sign heating equipment for that, for the worst possible case scenario? Because the design temperature is much less than that. It's not the average, because if we did the average, then we wouldn't be doing it to a low enough design temperature, because sometimes it's 10 degrees in January. So you can't do the average temperature. So what they've been doing for many years is the 2.5% January temperature. So that means that 2.5% of the time it's colder than that. The rest of the time it's warmer. So there's no point in really oversizing, considering that by design we're sizing for 2.5% of the time. There's a few different examples in BC. So Vancouver is -7, Victoria is -4, Prince George -32, Fort Nelson -39, and Soup -1. So Environment Canada gives us these. We get these from Environment Canada. Also on that sheet was a checklist for when defrost is required. There's no code requirement for that. So when is defrost required? When there's risk of freezing the coil. I would say anywhere in BC it's cold enough, even Vancouver, that you could get that -15 that it's been for a couple weeks. So it could freeze, so it's good to have the defrost. There's a little temperature sensor in the unit. that senses when it needs to defrost. So setting it up that it's able to defrost is just setting dip switches and controls generally. And it's able to defrost if it has to, but it's not going to unless it needs to. Box 4 is a list of where the air will be distributed. So on the design sheet, we write down where all of the exhaust air is going to come from and how much airflow we're designing the system for, and then the same for the supply, again with how much we're designing it for. Little fail-safe to make sure that all the boxes that are supposed to be equal or more than or less than are. Another little box that says the bathroom exhaust, continuous intermittent, for cable 93236, that's the one that says 20 or 50 intermittent. Supplier provided to each bedroom, so there's a spot to remind the designer that we need to have ducted air to the bedrooms, not necessarily dedicated from the HRV. You can tie into the other forced air system, but it does have to be ducted to bedrooms for the occupants. And supplier provided to each floor. If it doesn't have a bedroom, it has to have fresh air as well. So this again is the exhaust rate that you have to have. And then as far as supply rate, there's no code requirement, but there are recommendations from Natural Resources Canada. And they say that a master bedroom should have 20 cubic feet per minute, an unfinished basement, 20 feet per minute, and other rooms are 10 cubic feet per minute. Again, this is not code required, just a recommendation, but it's a pretty good recommendation. When I design them, I try to follow these recommendations. On to the next list. Bathroom exhaust, continuous intermittent. That was a model of that last one that I just did. And then appliance location has to be inside the thermal envelope. Access to drainage if required. Not connected to range hoods, cooktops, central vacs, or clothes dryers. It's amazing the things you have to put on a check sheet. When I saw that, I couldn't believe it, but you know, it's not there because somebody made it up. Minimum one exhaust inlet, at least 2 meters, like I showed in the code picture, so 6.5 feet above the top floor level, so the uppermost floor level. Exhaust stacks downstream of exhaust fans have no connections with other fans. Again, I can't believe that you have to put that in there, but you do. And kitchen grills have to be 4 feet or 1.2 meters horizontal separation from the range, or they need a grease filter. Close that door. And for that, check because local codes may differ. Locate grills, diffusers for fully dedicated systems only. Do not provide combustion or dilution air for fuel burning appliance. HRVs are supposed to be balanced, so you definitely don't want to be supplying makeup air or combustion air with them. It's air in, air out, and it's balanced. Ventilation is totally different than combustion air. So we're definitely not doing that, or makeup air for ventilation like we put in a bigger exhaust fan. Locate the HRV supplying exhaust weather hoods, a minimum of 1.8 meters separation so that you're not exhausting the stale air out and pulling it right back in again. And so they say at least 1.8 meters. Most manufacturers do have a single entry kit that are designed so that with one terminal, you can exhaust the air out and pull it in. They're very similar to a direct vent gas fireplace, where you get one terminal, it's exhausting the air out, and they're designed so that the air doesn't mix, and they're tested by the manufacturer to make sure that that doesn't happen. So there are, if you do see those, they are around the single port, or if you don't want to have two hoods, and you'd like, if you're a builder and you just want one, they are an option.
Technically, those don't make codes, though.
They do if they're tested by the manufacturer. Yeah, if it's tested by the manufacturer, that would meet code because it's CSA approved with that by the manufacturer. So it's when you have two separate ones that it would be. The way that we size ducts is we have to figure out what the longest effective run is from the weather hood, so the supply weather hood to the furthest effective length of the furthest supply diffuser, and then from the furthest exhaust grill back to the exhaust weather. We're sizing both sides of it. And what we do is we make a list of what all the fittings are, the different types of duct, because some isn't equivalent to 1 foot. We'll cover that in a second. And we make a list that's on the check sheet so that it's easy for inspectors. It's easy for the designer, the installer, and for the inspector to know that that is the longest run, these are the fittings on it, so it's good for a quick double check. It also has a formula for figuring out the rate that we use for sizing. And then there's an optional duct sizing, so you can put every single piece of ductwork and the size on the sheet as well. That's optional. We didn't have everybody have to do it. Once you know the friction rate, it's pretty easy to check the others, but it'd be nice to have people fill that out. And that was for exhaust, and then there's one for supply as well. And then there's a spot to draw. So if somebody wants to do a schematic or a ladder drawing of the system so that people could see the design as well, there's a space for that as well. And finally, a designer certification. So the designer has to be certified so that we know that they know how to size ductwork and equipment and the basic codes around them. So there's a spot for the designer to do it so that if there are any issues, you know, was it the designer, was it the installer, or was it the commissioner? It's set up to make people a little bit more accountable. So the designer has to be qualified and have a stamp. This is a system installation checklist. We'll run through that one. So a lot of the things are the same. So again, it has to be inside thermal envelope, circle whether it's hanging or wall mounted, in a serviceable location. So we have to make sure that it's in a location that people can find it, check the filter, clean the filter. Homeowners should know filters should be changed, cleaned a couple times a year. It's a constant running fan, so it should be at least checked and cleaned a couple times a year. So it should be accessible for that. That it has a drain or condensate pump, drain housing, trap, and not connected to, again, to any range hoods, cooktops, central vacs, or clothes dryers. And then B, the principal ventilation system designed to run continuously, so we only have continuous ventilation. We don't have intermittent ventilation anymore. Dedicated switch with 2 settings, on and off, so that can't be just the 24-volt control telling it that the fan isn't off. It's an actual service switch. Accessible for servicing, clearly marked principal ventilation exhaust fan. Sound rating not to exceed 1 zone for continuous airflow speed. And if there's multiple airflow options, a lot of them have like a timer that you can just press a button and it will click up faster. So dedicated switch, other than on and off, and activate it with a timer. The electrical, if it's hardwired, should be done by electrician. So the spot to remind them that. Electrician required, and that there's a safety disconnect switch. Partially dedicated systems have to make sure that the furnace fan is set to run continuously. So that'll be the drawback of the partially dedicated compared to the dedicated system, is the need to run that fan, a furnace fan, 24 hours a day. We'll talk about energy modeling in a little while. I have some slides that will show you the comparisons, and it'll make sense then. The duct layout, minimum 1 exhaust inlet for at least 2 meters above the top floor. Exhaust ducts have no connections with other fans. In the kitchen, it was 1.2 meters away from the range to prevent the core from getting clogged up with grease. Damper located in each ventilation supply and exhaust branch, and supply and exhaust main lines, so everything can be balanced. Duct layout according to the design, so if it was designed, did you do the layout the same way? And building airflow must be accommodated with door undercuts or air transfer grills according to BC building code. The door undercuts can get quite big if you actually figure out how many inches of free air you get. The little cuts that we get usually don't cut. Fire and sound separation for single-family dwellings that contain a secondary suite. Different municipalities won't let you do, so depending on the municipalities, some will not let you do an HRV to do the main part of the house and the second suite. Some will, some won't, so it depends on the municipality that you're in. If they do let you, the HRV ducting isolated from the main suite to the secondary suite, or the ducting extends from the secondary suite, and they want you to do proper fire and smoke, but that varies from municipality to municipality. My understanding is that most municipalities want your own ventilation system. So that one's kind of a gray area right now. Dampers have to be located in each branch, supply and exhaust, and located in each main line, supply and exhaust. That's the only way we're going to be able to balance it. So you have to balance the air in and out of the building, and also balance it to each zone to ensure that you're getting the airflow that you're supposed to be getting. Outdoor weather hoods installed as specified to manufacturer specification. Have to have a screen corrosion-resistant material with openings between 6 and 12 millimeters. And there's an installer certification. So if the installer is taking the certification course, they should understand the design and be able to do it and know when things are different than the design, and then make the changes accordingly. So the installer should actually be certified as well. If the designer is certified, the installer is certified, and the person doing commissioning is certified, we now actually have HRVs that start working, because a good portion of them now aren't moving the airflow that's required.
But the designer has to be certified, and the installer doesn't necessarily have to be?
They're supposed to be. Vancouver is the only one that's requiring these sheets now in the new year. They actually worked with us in developing them. We have a Vancouver-specific one. It's mostly just the SRE that's different. They want it a little bit more efficient. But my understanding is that they're going to be wanting the person who designs it, the person who installs it, and the person who commissions it all to know at least a little bit about an HRV.
Yeah.
It's a one-day training course. It's not a huge investment in time. It's a pretty intense training course. It's a fast-paced course. Most of our courses, because the trades don't want to take time off work, we've been asked to have sort of intense training courses, and they seem to work. People that get them. But they're not like a nice, slow-paced course. They're quite fast-paced courses. So, but in a one-day course, people can get the certification. They have to kind of know a little bit. You have to have ventilation guidelines as a prerequisite. And people that don't have any experience will find it a little more challenging to understand the terms. But we get most of the people pass it, the ticket. So this is installer certification. So the hope is that the designer, the installer, and the person doing the commissioning all have a little bit of training and understand the concept behind the importance of balanced ventilation, the importance of delivering the air to the proper zones, and the understanding of how to deliver the air to the proper zones. And then we have our balancing and commissioning sheet. This one's a little bit simpler. So to start for balancing, you want to make sure all the windows, doors, and flues are closed. So we tell them right on the checklist how to do this. So how to balance. So all windows, doors, and flues are closed. All other ventilation off. All grills, diffusers, weather hoods open and unobstructed. All joints and fittings fastened, sealed against leakage. And fully open all the dampers. Turn on the HRV.
So are all of these available on your website?
I'm not sure if they're there yet, but they will be. Our plan is to put them on the inspector's site.
Okay.
Are you an inspector? Or?
Yeah.
Yeah, okay. So yeah, they will be. If they're not there now, they may be there now. I haven't looked at that section. It's a pretty new section, but they will be there. If not, if you get in touch with us, we could send you a copy of them.
Okay. Yeah, for a regional district, it's very difficult to get any of this.
Yeah, we can, I'll find out if it's there, but after, if you want to give me your card, I can email them to you.
Yeah, for sure.
Yeah, anybody who wants them, I can email them to. So that's number one. And then measure your static pressure, measure your airflow. They want to know which instrument you used for measuring. Most people, the current standard is nobody's doing it. And I mean nobody is doing it. It's very, very unlikely that somebody has balanced it. A few people, but very low percentage of people are doing it. And then HRV remains balanced during furnace fan operation. So if it's a partially dedicated system, I get asked all the time, well, that furnace fan is really powerful. Doesn't it throw things out of balance? The reason it doesn't is because the ducts for the HRV are smaller, so everything is in proportion, it's relative. The duct pressure in the HRV is about 0.2 on each side of the fan. And the duct pressure on a furnace, if it was at 0.2 on each side of the fan in the actual ductwork between the, a little bit away from the furnace, that would be exceeding the capacity of the furnace. So the actual pressures are very similar. So that's why if it's done right, it doesn't throw it off. But we do have a check to make sure that it's done right, because if somebody doesn't have their ductwork sized properly and they're running a really high velocity or high static pressure, low velocity in their system, they may not be able to put the air in it. So you do have to check it, or it may pull it out of balance when it does come on and goes on high. So we do check to make sure. That's when it's tied into cold air return on a different type of system. And supply and exhaust equal to within 10% of in and out. So it's impossible to get it exactly, but you try to. So within 10%. And then there's the sheet there. So for balancing, so off of our design sheet, we would get the required airflow, and then we would get the measured airflow. And we're going to be measuring that with an air hood. Once it's done in the balancing and commissioning, there's little hoods that can be purchased. This one's fairly inexpensive, great for residential use. I think we paid like $1,100 for it. It's not a super expensive tool. People that are HVAC contractors should be definitely at least buying a basic model. It's just a 4-inch anemometer, and you just put it right over the grill, and it'll tell you how many cubic feet per minute are going through it. So we're able to test it, turn it down, open it, depending on what we want. And if they're bigger grills, we can smooth that. Does anybody know what we're talking about when we say inches of water column for pressure? Does anybody know what we're talking about when we say inches of water column when we're talking about duct pressure? So we're used to like your tire pressures in pounds per square inch. Duct pressure is about, it's a fraction of like, it's just a fraction of a pound per square inch. This is an old manometer. I'm not that old that I've ever used it. But it's just simply a tube with water in it. You set it to 0, and when you hook one side up to a duct, it will offset the 2 columns of water. And if it changes 1 inch, that would be 1 inch of water column. So that's what water column means. And it's just done with, you can actually still buy these, $35 on Amazon. Most people would use something more like that, which is an analog gauge, or the digital one as well. I've always used the digital. I like technology. The analogs are quite popular as well, because they're a little bit less glitchy, but you end up having to buy a bunch of these to get the scale, or you just need one of those. So our, whoops. So we put our required airflow, measured airflow for each zone for both exhaust and supply. If people do that, then their HRV may be working. If you're getting the balanced ventilation, and if you're supposed to be taking, if people aren't putting in an extra bath fan, and they're supposed to be getting 20 CFM for code, there should be 20 CFM coming through there. And from the systems that were looked at, there's not many that are actually doing what they're supposed to, which is why the city of Vancouver really pushed for getting a course for installation design and having a check shop. And hopefully the other municipalities follow suit, because it makes a big difference. Some of the builders have found out about this. I've been getting calls, people asking, will I come by and double check the installation to make sure that it was done right for people that don't need the sheet. So I referred it to somebody else because I just can't do it. So, but there's definitely a need for it. This is the energy modeling. So it was done by RDH, they're an engineering company. And the light purple shows your ventilation heat that you're saving, or the cost of your ventilation heat when you compare them, that's what you're saving. And the darker one is the fan energy. So if you look at the first one, this would be ventilation system number 1, where it's a forced air heating system with a 4-inch duct tied into the cold air return, insulated vapor barrier to its full length, tied in between 10 and 15 feet from the furnace cabinet, and then your principal exhaust fan typically is a bathroom exhaust fan, set to run continuously and to meet the exhaust requirements of 93235. So that would be what that system is. If you compare that to an HRV and a furnace fan, notice how your energy savings in your heat has gone down a little bit, but your fan energy has actually gone up because you're using the fan in the HRV, the 2 fans in the HRV, which are small fans, and then the large fan in the furnace as well. When you compare that to an independent system, notice how low the HRV fan is. So there's big savings, or bigger savings, when people use an independent system. So whether or not they have a duct system, if they don't have a duct system, then they're definitely putting an independent system. But if they do, most people, because of savings in installation, will put in a combined system, or partially dedicated. And then you end up paying extra energy to run your fan. If you compare this to that, paying the HRV, or the heat portion is pretty much the same. But look at the difference in your electricity for the fan. And then it compares it with the CRV and passive inlets as well. Passive inlets is lots of energy exhausted out in the heated air, but there's no fans to bring it in. That's only allowed in certain applications. Most people don't really like to have holes cut into their bedroom to the outside. So I think you'll probably find most of those disabled after the inspector leaves. And then this is a different climate zone. So climate zone 5, a little bit colder, so you can see that there's more. It's the same format with the different ones, but because it's colder, there's more savings involved. And then for climate zone 6, climate zone 7A. So there's quite a bit more savings when you start getting into the colder temperatures. These are based on, this is your ventilation heating, so this isn't your fan, this is just your ventilation heating, not the fan savings. And in climate zone 4, for a 4,000 square foot house, you're looking at about 190 a year, 227 for zone 5, 279 for zone 6, and 380 for zone 7. These are based on electric resistance heat, so probably about a third of that if you were to do natural gas. Compare it with natural gas. So the energy savings isn't going to pay for it anytime soon. The advantages of an HRV are balanced ventilation with less air going through your building envelope and being able to put that air, which is already tempered, where you want it and exactly how much you want it. That's the big advantage of it. HRVs will take some time to pay for themselves compared to the other. I don't think they would have a payback. Here's some Canadian comparisons. So if you're comparing it with natural gas, in Vancouver, it's about 20%, but that's only $50. So again, not a huge savings when you're comparing it with natural gas, but if it's electric baseboard, the savings is a little bit higher. So we have to make sure that the equipment is installed within the building envelope. Ductwork's recommended to be installed within the building envelope. There's all kinds of bad things that can happen if it's not. If the supply duct is installed outside of the building envelope and it leaks, you're taking air out of the house and you're not putting back in. It's like having a big exhaust fan. So you're putting out your conditioned air, but you're also creating a negative pressure in the house, which can cause some problems. When ducts are to be returned to living space in unconditioned and ran through unconditioned space, insulation value has to be the same as the above grade wall for that zone, which would be here. So depending on the zone that you're in, the walls would have to be either R16, R17, 18. Also, for the insulation requirements on the HRV, from the weather hood, running through conditioned space, bringing in the cold air, you have to have R4 insulation with a vapor barrier to the unit. Once you go through the unit, it's conditioned air in conditioned spaces, so you don't have to have any. On the way out, again, you don't have to have any insulation because it's air from the house. It's pretty much the same temperature. It just has some moisture and it's stale. And then when it's going out, it has to have R4, but it doesn't need a vapor barrier because the vapor barrier goes on the warm side, and in this case, the warm side is likely the inside. If it's running through a unconditioned space before it goes to the conditioned space, this part of it will be the same. So R4 with a vapor barrier R4. Where it's coming in, you don't have to have any insulation until it hits the conditioned area, because the air out here is going to be the same temperature practically as the air in there. So you're not going to get any sweating or anything like that. It'll be within a couple degrees if it's just an unconditioned space. Other than exposure to wind, it's pretty much the same temperature. And then with the air going out, you would definitely want to still have the R4 because it's going out through the cold space, and you want to make sure that you don't get sweating coming back. The material used for installation can make a big difference in the system's performance. There's a penalty every time that air changes direction. So if there's 90-degree elbows, wall stacks, 45s, there's different equivalencies if you were to compare it to a foot of smooth rigid duct. So we compare everything to smooth rigid duct of the same size. So if we're comparing a 90-degree elbow, that's going to be equivalent to 15 feet of smooth rigid duct of the same size. If we're comparing a 45, that will be, again, 5 feet of 1 foot of, or 5 1-foot sections of smooth rigid duct. T's are quite restrictive. When you change direction, if you go this way, it doesn't do anything. But when you change direction, that's like 60 feet. And then a Y will be 35 feet. So if possible, Y should be used. It's half of the restriction. As people are adding those up on that slide that I showed you where we're finding the longest effective run, the more restrictive fittings they use, the longer the run will be, the bigger all of the ductwork will have to be. And then my favorite, flex duct. Is flex duct everybody's favorite? It's quick and fast to put in. There are applications, if it's sized right and installed properly, there's a place for it in the industry. It's good for preventing sounds from transferring, vibration. It's already insulated, it has a vapor barrier, but most of it isn't installed properly. This table, go to the ASHRAE manual, and it shows, so this is your diameter of flex duct, and they have two different velocities. So the air is going slower when it's going in a branch. It's closer to where you're going to hear it. So branch velocity is about 500 feet per minute, where trunk velocity can be up to 1,000 feet per minute, 900 to 1,000. So at a 500 feet per minute or 1,000 feet per minute, we'll have different rates. This is the diameter of the flex duct, and this is the equivalent length. So there's a rule of thumb. We say in the industry that a foot of flex duct is like 2 feet of regular duct. Keep in mind, that is when it is fully extended. Not when it's only 90% extended, now it's suddenly almost 4 feet for that 5-inch duct instead of 2.2. All of these are pretty close to 2. And the other rule of thumb is you increase one duct size. So if I had 5-inch, it does what a 4-inch would do. 8-inch will do what a 7-inch will do. 12-inch will be, that's almost 11. So that's where that rule of thumb came from. But again, look what happens to it when it's only 90% extended. And then when you only go 70% extended, which would be fairly common. I have a display that I use for the HRV. There's a slide with a picture in it. And I take it around to different things for the HRV course to teach balancing. So we show people, there's eight drills on it, actually 9, there's another one that's not on the board, it's in a different place. And I tried to make it portable by having 3 modules and flex duct going in between it, and I wasn't able to make it work. I couldn't get enough airflow with doing it without putting on, like, it was supposed to be 5-inch duct, and I tried 6-inch duct, and it still couldn't get any airflow through it. And it's because it wasn't extended and, stretched out. It was just looped around. And I just couldn't do the display like that. I had to do it with our duct. So it'll be interesting as people have to start actually showing and proving that this amount of air is being delivered. So if you take a piece of 8-inch flex duct, fully extended, it's equivalent to a 7-inch pipe. Using our duct sizing table, and I picked a common, the friction rate is always different, but as long as my comparison has the same friction rate, so it'll be a good comparison. So at a friction rate of 0.08, a 7-inch duct will move 142 cubic feet per minute. So that's what people will be thinking when they design it. Now let's say that it's only 90% extended. Now it's twice the equivalent length, and it's even smaller. It's gone down in size. Now it's 2 sizes smaller. It'd be like a 6-inch. It was actually a little under 6. 93 CFM. We thought we were getting 142. We designed it. Now we're only getting 93. The more likely thing would be that 8-inch flex is 70% extended or less. Every foot, when it's 70% extended, is equal to 15.2 feet. And they're pretty close. If it's smaller with a 5-inch, it's actually 16 feet. That would be why most flex duct systems don't work, because they're not sized properly and put in properly. And if people have to actually show that they work, I think they'll be reinstalling it fairly quickly. So now we're looking at a 4.5-inch equivalent. Same friction rate. Now we're down to 46, almost 100 CFM less than we thought we had. The fan will be using the same amount of energy trying to move that, but it won't be able to. So we take a list of everyone from the weather hood, count up all the 90s through the unit, more 90s, a Y, if we have wall stacks, going up here. In this case, the T, because that has 60 equivalent feet, will likely be, and it has a 90, that has a 90, that is a 90, that is a diffuser, that is a diffuser. So the difference is in the measured length, but this is actually your longest run, because that's 60 feet just in that T when you change direction. When you went straight through it, it wasn't. So we add up all the pieces, and it tells us what our longest effective run is. We transfer that to this sheet, and there's a formula on the bottom that tells us how to turn that longest effective run into something we can actually size ducts with either the duct sizing chart, or has anybody seen ductulators? I've seen a lot of people using them, not many people using them right. This is based on that ASHRAE chart, and you just set it to your friction rate. It'll tell you your round duct size, your rectangular equivalents, lots of information on it. It's based on 100 feet of duct. Keep in mind that one exhaust row is 100 feet of duct. So every house has more than 100 feet of duct. So anybody who just uses this and uses the recommended setting that they have on it is not using this correctly, because every system is more than 100 feet of ductwork. So with this, just like I was doing before, we select a friction rate, we determine how many CFM are going through it, follow that over, it tells us the size of pipe. So every single piece of pipe in that system has to be sized. No more rules of thumb than a gut feeling. If people have to be accountable to show it's going to work, hopefully they're going to be duct sized. All the joints have to be sealed. That includes the seams, the gores, every single part of it has to be sealed, because we're not allowing for any duct loss, any air loss in the duct size. This is the door kit for balancing in and out. When I bought this door kit, the supplier that I bought it from, who sells this HRV, ordered it from Calgary because nobody's ever bought one before. What does that tell you? Nobody's ever balanced their units before, because you need this door kit to do it. How are you doing it? Nobody knew. You're supposed to do that? Manual, just never read that. What that's doing on each side, so you see the door ports here, we're measuring the pressure. There's your fan in here. We're measuring on this side of the fan and this side of the fan. So that's how we're able to measure the resistance that this fan has to work against, all the way through from the weather hood to the exhaust hood, or from the weather hood to the supply. And same for the exhaust. They'll have different readings, and then there's charts. There's charts in the manufacturer's book that tells you Depending on the fan speed you have and the pressure, will tell you for supply and exhaust how many cubic feet of air you're moving. Put balancing dampers. Typically the units come with balancing dampers on all four, the in and outs on the unit, and then every branch line has to have its own damper as well, which is typically a diffuser. There are zone systems that are a little bit nicer with the diffuser. I usually put some Loctite or something so that once I get everything balanced, somebody doesn't come along and say, hey, what's that? With one turn, now the whole system's out of balance. So it's good to lock those in as well. The unit will have an approved static pressure that it can run after, or run on, so we're needing to measure those. I use static pressure ports when I do it, along with my manometer, and they're just simply testing the pressure that's in similar. It's the static pressure isn't the air moving; it's just the pressure. Think of a balloon, and it's measuring how much pressure is on the duct on the inside. From that, it helps us to determine how much air is going through it. Before it's drywalled, people should be checking to make sure that you can get the 20 CFM from the room you want to get it from. You can put the air where you want to do it. This is a flow grid. It's checking the static pressure, the total pressure, and from doing that is able to give us the velocity pressure, which gives us our true airflow. These could just go on a duct. You can either leave it on for quite, for $100 or so. You probably don't want to leave them on, but you just put it on, test it. Yes, it will do it. Take it off, and just put the duct back together. So they are able to. It's not like a crapshoot that. Sure hope when that drywall goes on that this worked. If they sized it properly and then double check to make sure the static pressure and the airflow rates, they should make sure that it's doing what it's supposed to do. So that's the flow grid there. And this is our demonstration model with the little that. And you're just opening and closing registers until you're getting the reading that you want. The last thing that has to be done is we have to go through the entire thing and make sure that we have to go through an entire cycle and make sure that there are no changes necessary. Because as soon as you change one, it changes everything else. So as soon as you close one, more is coming out of it. So you thought you had 20 coming out of it, and you close them off, and now you have more. So you have to change them and go through. It takes some time to do that. There was a guy who actually all he does is system balancing that was in one of the classes, and he said typically it's a better part of a day to do that, to do a proper balancing. So system design is going to take time, and it's installing it properly will probably take more time, and commissioning it and making sure that it does is also going to take more time. People don't typically want to spend the time, but why are they putting in an HRV? We're not going to balance it. It's not doing its job. It's not providing the ventilation it's supposed to. So it's very important that it be balanced. There's different controls. Some are just the way they are. They just run constantly. Timers where you just press a button to make it come on so that you can have, like in a bathroom, if you want the air to be a little bit faster, you just press a button, it'll come on for like 20 minutes or something, and move a little bit more air, then go back to its original. Some do dehumidification, and if it gets too humid, it'll bump up to the higher speed. There's some that are fancy, programmable, you can do balancing on them. There's some it depends on the manufacturer. They all have really fancy ones that can do more. So they may even be able to balance it by or at least part of it, instead of a door kit, they may be able to use a control. And they'll just list how they balanced it on the sheet. But the control would only that's not going to do each zone. That's only going to do the in and out. And that's what most manufacturers' manuals will say in their instructions of how to balance. They're just telling you how to balance so that the air in and the air out is the same. We take it a step further than that by actually wanting to know how much air you're delivering to the zone and how much air you're taking from the zone to make sure that it truly works. Let's talk about humidity. So there's absolute humidity, which is the measure of the actual water vapor in the air at a given temperature and pressure. So let's say that 25-degree air can hold 20 grams of water at sea level. If you were to change the temperature of that air, then it's not 25-degree air anymore. So absolute humidity isn't affected by temperature because it is that temperature. If you were to cool that to 20-degree air, then you would have 20-degree air, not 25-degree air. So you would have a different absolute temperature or humidity because you have a different temperature of air. So the absolute humidity is for a temperature and pressure of air. As soon as you change it, you have a different temperature and pressure. So that would be a different, but it doesn't change. That is the most amount that air can hold at that temperature or pressure. Relative humidity is a ratio of the absolute humidity to the theoretical maximum for a given temperature and pressure expressed as a percentage. So if it's 40% relative humidity, that means we're 40% of the way to where the air can't hold any more water. 40% of the maximum of that temperature of air. We have sensible heat, which is the temperature energy of the air. It's typically measured with a thermostat. When we see the temperature changing, the temperature we see on the wall, that's the dry bulb or sensible heat. There's also latent heat. All the air has water vapor in it. It took energy to turn that water vapor, or that water to water vapor in the air. That's why it feels hotter when, if you're 23 degrees here compared to, let's say, 35 degrees in Kamloops where it's drier. It doesn't get uncomfortable there until it's like 38. Can you imagine if it was 38 in the lower mainland? It's like 80% humidity. People wouldn't move. It gets 24, 25 here and we're complaining it's too hot. Water vapor gets into the air through either evaporation, so the surface molecules get enough energy from the air to escape and become a gas and they evaporate, or from boiling, cooking. You could see it actually when you're heating up a pan or have a glass kettle that has a little element in it. You can see the bubbles form on it and then go up, exactly like this picture shows. We talk about sensible and latent energy. It takes, definition of the BTU is the amount of heat required to raise a pound of water 1 degree Fahrenheit. So it takes, to heat this water from 211 to 212 would be a pound of water, would be 1 BTU. To heat that same water once it's 212, to still be 212 but turn to steam instead, is 970 BTUs. It's quite a bit of energy involved in changing the state. That's how air conditioning works. We're getting into this more to understand the latent and the sensible, to understand how can we reduce the humidity in a house by bringing in 100% humidity air when it's raining. I get asked that all the time. It's raining, how are we going to reduce the humidity in the house? So going back to our psychometric chart, anybody used these before? We're only using a portion of what they can do. 25-degree air at 30% humidity is 8 grams of water. Sorry, that's 40% humidity. 40% humidity, 30 is over there. So these lines here are the relative humidity. It'd be 8 grams of water. If that was to go up to the saturation point or dew point, 100% humidity, you find there'd be 20 grams of water in that air. So 20 grams is the maximum amount of water air can hold at 25 degrees. 8 grams is 40% of 20. So the relative humidity is 40% if the air can only hold 20 grams. The 25-degree air, when it's cooled down to 15-degree air, is now at 75% humidity. So it changes when you cool it. So if you cool it too much, you're going to get condensation. So it's good if people have some airflow and are able to pull cold air from different places. 10-degree air at the saturation or dew point, heated up to 25 degrees when you bring it in. So let's say it's raining outside and it's 10 degrees and it's 100% humidity. When that air comes in, it's only 40% humidity down. So that's how bringing fresh air from outside is able to reduce the humidity in a home. When we're designing it, you want to put the supplies where they'll actually do something in the room. If we were to put it right here, there's not going to be much use in the room before it's out of the room. So we try to put the supplies in where they'll actually serve the room. keeping in mind that we really want to avoid, even though we temper it, we want to avoid having it in locations where it's going to blow on the occupant. That could be 50-degree air, 50, 55-degree air. Nobody's going to want that blowing. Different types of defrost. This is a fan defrost, so what it does, there's normally a supply fan that's bringing in the cold, fresh air. If you turn off that fan and just exhaust it out, that'll melt any ice that's built up in the coil. That'll defrost the coil. Another's a damper. That's the most common that I see now. And what it does is it dampers it off, and again, the air that should be exhausted just comes around and is back in as supply. You would think that would have some really negative effects, but it's such a small volume of air that it really, and it doesn't take very long to defrost it. I've never heard people complain that they're getting smells or anything like that from it. Another method is a fifth port, and that's where there's actually a fifth port, so you can choose where you take the air from the home. You have to be careful that that doesn't get installed in a furnace room with a B-vented appliance. Any naphtha appliance, have to be careful of the areas that you're depressurizing. The drain. The best way to do a drain on an HRV is to have the T-point up and around. The whole purpose of this drain is to prevent that airstream from mixing with this airstream. Most of the time when you see an HRV drain, it has no water in it. So if anybody's using that to protect from sewer gases and tying into a drain, they're going to have to be pulling in sewer gases as part of their airflow. So they're not meant to stop sewer gases, they're just simply meant to prevent this stream from mixing with this stream. So if the T is installed pointing up, this will stay full of water, which should be done when the system's put in to prime the trap to make sure that they're not sharing airstreams. And then when it's serviced, it should be checked to make sure that there's water in it as well. Homeowners should probably be educated too that when you're cleaning your filter, check to make sure that trap has water in it. If not, take a picture of the water and pour it in.
That wouldn't be a direct connection to your sewer anyway.
Yeah, it's supposed to be indirect. So that's it for the slideshow. Any questions?
Yeah, you talked about the controls on the wall there, and the code requires the HRV to run continuously.
Yes.
Does that control allow them to shut the thing off?
No.
Okay.
No, because the ventilation in BC is continuous. In Canada, it's continuous.
Right.
So you're not allowed to turn it off.
So
What
exactly is the control doing again?
It boosts it up. Let's say that you have 20 cubic feet per minute coming out of your bathroom, and you want to have more. There's a little timer control. They can either do.
Usually it boosts it to like 50.
Yeah, they can either
It
do.
takes the full CFM and then divides it by the amount of bath fans, essentially, doesn't it?
It depends. There's zone systems where diffusers will open and close. So if you're in one bathroom and you press the button, that one will open, the other one's close, and you can get more air coming from that particular zone. The more common way to do it is with a timer. So I'll just go to that slide. So with a timer, this is a pretty basic control here. So there's a fan, you turn that on and it's just going to bump it up. That would just run indefinitely on high. This one here is a dehumidistat, and one of them is a timer as well.
Okay, so but it's still running at its.
You have to have a minimum.
Requirement.
Yeah, so your 93235 minimum has to be your low speed, and if there's any timers for intermittent operation to boost that up so that it can get more of the air. A lot of people like bathrooms in particular to be exhausted very quickly. So if you press a button, a 20-minute timer or something that will come on, and instead of it doing 20 CFM, it could boost up and do a little bit higher. Without a zone system, it'd be pretty unlikely that it goes up to the 50. So the people that are saying that it's their bathroom ventilation, the minimum 20, it's good that they're going to have to start proving that, because I suspect that most of them aren't taking 20 CFM out of the bathroom. You see some systems out there that have like 9 outlets for 60 CFM. I don't know how many CFM they plan on doing it, but when you divide 60 into 9, you're not getting 20 out of any of them. So people should, hopefully with the design sheets, that will take care of that, and people will actually be doing, like if they're running an exhaust vent, they'll actually do something, especially if they're counting on it for being their primary ventilation for the bathroom. If they don't want to put, a lot of people don't like to put bath fans in. Some people do. I think it's mostly common that they do both, but a lot of cases they're not putting them in. And I think as we go, we'll probably have less and less just exhausting out air without trying to temper it coming in.
That's kind of a double-edged sword too, though. We built, when I was building, I was in Whistler, and we built townhouses there and didn't put bathroom fans in, only put in the HRVs.
Yeah.
And then, like a year and a half later, we got called back. Apparently the power went out, the HRV never restarted, and all of their fixtures in the bathroom were rusting.
Oh, wow.
Because the owners didn't think to go downstairs and check it. And there isn't a secondary fan. So we basically just lived without a bathroom fan for like a year and a half.
It'd be interesting to see as well with one of these flow hoods, if you're not putting in an extra bath fan. In most cases, if there is a bath fan, that's probably going to take care of your intermittent, because they don't really make bath fans at home. You don't really see bath fans that are under 50 CFM very often. I guess there are some, but they're fairly uncommon. It'd be interesting to see, and hopefully people start proving that it's actually taking that 20 CFM out, because I would think there's a lot of them that aren't. And people are counting on them for their primary ventilation. And 20 years from now, when they get sick, they may figure out why. It'd be really interesting, like in your townhouse, to take one of these and see if it's actually removing the code requirement of that room.
That would be very interesting.
Yeah. I would be willing to bet that it's probably not, but it may. It depends. It depends. There are contractors that do good jobs. I end up seeing a lot of the bad jobs, so getting involved with those. So. Any other questions?
So when I come to do a final inspection and it's not plugged in, it's a pretty good guess it didn't get balanced.
Yeah. Yeah.
Actually, about 20% of the time, when you get to the final, it's not even turned on.
Yeah. It probably never has been.
And some of the times it actually isn't plugged in.
Yeah. Yeah. Yeah, I've seen a lot of equipment that was supposed to have been commissioned that absolutely couldn't have. And if you know the trade, you know that, well, that wasn't done, but people will. So now if people do that with the sheets, at least if you call them on it, they'll have to come and prove it. And if it's not even close and they can't make it close for you, then you get to say, you lied, because that's an affidavit that you're stamping and saying. And we also have included in our course the ability now to remove somebody's qualification. We've only had to do it once so far, but once that happens, their name's going to be on our website. They're going to have to get recertified. People will catch on. I mean, you'll know if they just get the other guy that works for them to fill out the forms. You'll know that pretty quick. They really won't be allowed to do that. So we've been asked by one of the municipalities to make it so that we can take away ratings, to give a little bit of teeth for doing it right. So if people are out there signing sheets saying and putting their stamp on it saying 20 CFM out of this bathroom and there's 3, it can be within 5 CFM, keeping in mind that if the code says 20, it has to be 20. So you can't go lower than the code required amount coming out of the room. The air into a room, the code just says you have to put air in a room. That'd be a little bit harder to catch somebody on, but still the air has to go somewhere.
Yeah, the fortunate thing is that it's not mandatory that they get the certification to begin with.
Not yet.
Right. Yeah.
Not yet. Vancouver's making it mandatory, and from what I can see from most of the municipalities, I've talked to other municipalities that are starting to use our paperwork for their forced air heating designs.
Yeah.
They're not doing anything with the paper, but they're at least collecting and getting people to fill it out. So until all the inspectors get trained on what to do with it and the plan checkers, it's kind of hard to do it. And there is a thing as well that I guess you can't take people's livelihoods away from them and shut the whole industry down and say all of a sudden, all you people who don't know how to do things have to be certified, and then if there's no time to do it. So there's lots of time. People are being told that they need to do it. It'll be a big surprise for a lot of contractors in Vancouver that aren't paying attention when they find that they're
So
not
when
allowed
does
to
it
do
come into effect
HRVs.
here?
Vancouver's the new year. Any
And
permit
are you thinking
after
other
the new year.
centers like Kelowna will follow suit, or?
Kelowna's really big on our forced air paperwork, so hopefully they do. It depends on the municipalities. We're showing it to the municipalities now and the different inspectors. Most inspectors want a means of inspecting and know what's wrong. They just usually don't know what's wrong about it. So this really gives the, with those sheets, pretty much everything they could do wrong is right on that sheet. So if they check it and say, yes, I installed it inside the building envelope and it's installed in the attic, that'll fail. If they say that they balanced it and somebody calls them on it and checks and it can't be like they can't show them. It's one thing if it got knocked out of balance, that could happen. Somebody else could touch a register, something could happen. But that person who said it had that many CFM has to be able to show you, maybe somebody changed a speed or something, but they have to be able to make that come out because they've signed an affidavit saying that that's how much air is coming out of it. So if they don't, there's something that can be done about it. So that would be up to the different municipalities and inspectors whether or not they adopt it or push towards getting something in place that makes people more accountable.
Just makes it easier for, well, especially for me, like I'm from a regional district, and it makes it a lot easier once it's mandatory that they get it, because we're in the Wild West in a lot of ours.
Oh, it's like that everywhere.
We don't even have building inspection in a few of our areas.
Yeah. What area are you from?
Columbia-Shuswap Regional District.
Okay. Yeah, I've done quite a bit of work in the interior with Thompson. PNRD. Yeah, done lots of work with them. And there's some areas. I did a job in Princeton, I think, and I tried to get like the plumbing permit. And they're like, there's no plumbing permit. I couldn't believe it. You just do whatever, and it's like,
Well, we just brought inspection into like our heaviest populated area in Line Bay, Sorrento area this year, and there's been quite a lot of pushback.
Yeah. And there is, and I see it like when I'm involved in a couple of different programs, and we'll be doing seminars and telling people you have to start doing heat loss e-gates. And it's been code since 2015. We're talking about F280-12, like 2012. It's been code for almost 5 years. People should start doing it. And in order to get people to do it, you have to pretty much give it to them. And then we'll see what happens now.
That's why I was asking if it's available, because we have to give out all the sheets that we expect to get back.
The sheets are definitely available. Definitely available. If there's anything that you would like to see available, just get in touch with us at PECHA and just let us know if there's anything that you would like to see on that inspector area. If there's something other than sheets, or maybe something where people can post comments, ask questions, any ideas like that, let us know. We're just developing it, and we're developing it for you. So we can do lots. We want to work with the different building officials and municipalities. And we've been out educating builders and on the flex duct and things, and letting builders know, because a lot of times they don't know why it's better to do one thing than another, or a lot of times as well, it's not even going with the lowest price. There's people charging the same price to do half the job. They just market better. You must have a question.
Actually, I apologize. I missed the first little bit of the presentation, but it looks like there's a sheet similar to the ventilation checklist sheet.
Yeah. There's. Let's go to the sheet with it.
Is that available on your website?
It will be if it's not now. It will be very soon if it's not now. It's still in progress. So there's sheets for design, installation, and commissioning. So that hopefully the person that does the design is qualified to fill out the sheet, and they need to have a stamp to do it, which should increase the chances that they're qualified to do it. And we're talking about a one-day training course. This isn't that they have to go take a 4-year apprenticeship. This is a one-day training course that they have to take, and we'll even go to them. So there's one for installation, or one for design, and then the installer has to have one as well, and the person installing has to stamp to take responsibility for it, and then the person doing the actual commissioning is supposed to stamp it. So that they at least know how to size ductwork, where the exhaust grills, supply grills are supposed to be. The ductwork is a big portion of it. We spend half a day learning to size ductwork, the equal friction rate, and then going through examples and everything. It's probably it's more than half duct sizing. So, and duct sizing is something people just don't do. If it has a 6-inch outlet, it must take a 6-inch pipe, right? Not necessarily.
Just like bathroom fans, everyone tries to go 4-inch up to.
What's that?
I said just like bathroom fans, everyone tries to go 4-inch up to.
Yeah. Yeah, and there's limits to what you can do, especially like you saw with that flex duct. You saw the flex duct portion of it? Yeah, we've been showing that to building officials and builders, and to contractors as well. It's part of the HRV courses. There's a lot of people who come and take our courses and are just amazed at that, because you would think it's 2 feet for every foot, right? But that's only if it's 100% extended, and it's typically not. Usually people take the roll of it and they stretch it out, or coupling 25 feet together and have like a 50-foot run of 5-inch flex duct. There's zero air on the other side if they do that. Yeah, well, hopefully it will. And if people adopt this, people will have to prove that there's airflow. And that's exciting, that HRVs will actually work, because the majority of them don't. There's one municipality that went out and looked at 15 systems, and guess how many didn't work? All of them. 15 of them did not work. So that's the reason why we're doing this. Because people are putting it in, and it's not, if people's heating doesn't work, you know it because you're cold. If your plumbing doesn't work, you know it because you're flooded out. If your ventilation doesn't work, you find out about 20 years later when you have all these diseases. And that's the big focus on air quality now, is people getting sick from ventilation, both commercial and residential. We're sealing our houses up tighter and tighter. We're supposed to be ventilating them. And people pay to get them ventilated. People are paying to put HRVs in, and then people are putting them in and not balancing them, or putting them in and not sizing them properly, or putting them in.
People, the owners are just putting their trust into the installer.
Exactly, yeah. And you would think when you call a big company that you're getting the best in the industry out there, and most people are not qualified to put them in. They just know how to put metal together, or a lot of people doing the flex duct systems who don't even know how to put metal together that are doing them. So, and again, flex duct does have a place. It's not, I'm not saying it's bad. It's just bad to build whole systems out of it undersized and not installed properly. If people want, you know, as long as it's not, they're not counting on the R4 insulation to take care of the attic, which you see that a lot. That has to be equal to the wall insulation, which is available now in like a wrap, foil wrap with fiberglass. They have R20 insulation. So. But hopefully people don't let ductwork in outside of the building envelope. I'd be more concerned about the lower pressure. Because once you take air out, if you don't put it back in, you create negative pressures, which really throws everything off. What's that?
Air doesn't move so well.
No. Nope, not at all. Any other questions? And that'll be it, I guess. I'm around for a bit if anybody has any questions, if they didn't want to ask, or think of it in a minute. I'll be around for a bit and be helping put that away in a few minutes.